Then let's continue talk about the comparison. In practice, since the hard disk is slow, running time is basically the time spent on the disk operation. Thus, the time is n divided by b times log m n divided by mb times d. I think it's not very understandable. The d is time for the disk operation. It's understandable. And the quick sort uses the O(n) divided by b times log 2(n) divided by b times n times. Okay, let's continue talk about the numerical example. What if we want to sort n equals to 40p and in 4 MB of RAM with b equals to 4096? The external merge sort will take m equals to 4 MB divided by 4096, which is equals to 1024, and log m n divided by mb is then log 1026 to the power log with the base 1026 to 1026, which is equal to 2. That's why using 3 recursive calls and 4 scans in total. The internal quicksort log 2n equals to 42, and we are using 42 recursive sort and 43 scan in total. And then we're going to tell an example of select program G401 students. Selection can be performed faster if we know where to find the row G401, and we're going to use indices to take the value of the one or more attributes of relation R, provide a quick access to the tuple with these values. For example, we can have the indices, we can have the attributes program, we can have the sorted value for the program, and then we can have some indices for the corresponding tuples in students. The secondary is merely the points to location of records in the disk, and primary in addition defines how data is stored. There are two kinds of indices. Good when attributes involve primary key, so merely points to location of the record always dense. I'm not sure this dense. And as a B plus tree is a kind of indices with secondary index, right? And then we're going to talk about the example revisited, where we select this G41 from students. The index of attribute program, we have the values, and first we find the entry for G41 index, and visit all the students G41, and visit all the students whose ID occurs in this G41. What is the difference between the original one to this one? It's just storing some pointers and then trying to get all these pointers within this G41. And for example, we want to find the program to G41 equal to in the students. We first find the entries for G41 and 2 in the indexes and in the index for program year. We visit all the rows in the students and whose ID are both in the index entries. So here's an example where we have student ID, name, program year. I have the modules, module code, module title, program year. Which indices should be more useful to find these queries? It's definitely this one, right? It's this one to be more. And we have We firstly find all the indices and visit all rows whose ID occurs in both indices entries, where we find this 2 and 2, and then we get this G41. Therefore, we only get this G41 Anna. Yeah. And then we're going to talk about the form of indices. We have the B plus tree, which is good if selection conditions specify a range, which says the program equals to G41, yeah, greater than 1 is the most widely used. We can create indexes on students using B tree, program in the year, and we can use hash table, good if when selection involves equality only. Create index on students using hash. Create index on students using hash. Lower name. What is this lower name mean? And simple level with multi-level indices, where we have the single level indices are stored in single list, multi-level indices stored in the distributed across different layers. The values and pointers is called single value, single level indices, and this is called multi-value indices. And then we're going to talk about B plus tree. It's in the multi-level indices, but different shapes than one shown in the previous slides. The shapes of a leaf in a B plus tree. The pointer goes to tuples in relationship with value for tuples in relationship with 82. Tuple. This one denotes the tuple, and this one denotes the next leaf. The B plus tree leaves. The idea is that what are these actually? What are these? Stored in an increasing order. They're pointing to tuple. They are values, okay. They are values, they are pointers. Values and pointers. And the pointers point to the tuples with the value A1. And points to tuples with the value A2. But this A2 is here, right? And pointers to the tuple n equals to chosen such that the nodes face into one single block. That n such that the nodes face into one single block. For example, disk block size equals to 512 bytes. The value is 4 bytes integer, and the pointer is 6 bytes, where n equals to 42. How to calculate the relationship between them? And the B plus tree, the inner node is that we can point to nodes where the value is less than A1. Oh, I see. So it is the same, right? Point to tuples with the value A2. Oh, this is points to the value which is less than A1. This points to nodes for values greater than A1 and less than A2. Points to values which is greater than an minus 1 and less than an. Points to values that are greater than an. Okay, cool. So the pointers point to B plus tree node that's the level below n chosen as before is greater than 1. So I have there are 2 pointers. Not all the files need to be used. There are some things that can be unused. And points to value with value A1, A2, and so forth. In short, at least n divided by 2 pointers are used. And for the I will ask why it's 2 again. Similar to the leaves, to ensure that at least the n plus 1 divided by 2 pointers are used. This session, the root has 2 pointers.